Okay, so let us begin with chapter 7. So we'll try to finish it today because chapter 7 is well, I wouldn't say it's a long topic. Okay, and according to a planner, you should finish it within 1 hour. All right. So chapter 7, gravitations. So gravitations is also a types of force. Okay, it will also cause types of force. So that's why when in move force, we are going to look at the Newton's law. Okay, we're going to look at the Newton's law. So first, 7.1, gravitational force and field strength. So 7.1a, state the Newton's law of gravitations. Now you want to look at what is the relationship between gravitations and Newton's law. So according to Newton's law of gravitation, a point mass will attract another point mass in any part of the universe with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Now, what does it mean? It means in this universe, on Earth, okay, whenever you have two objects, let's say this is object number 1, this is object number 2. Now, if you recall what have we learned in the previous chapter, every object come with mass. So they have a mass 1, mass 2. Now, this object, it doesn't mean that it must be a non-living item. Okay, it could be you and your friends. All right, it could be you and your friends. It could be you and your books, your laptops. As long as there are two masses, then there will be a force in between them. And that force, that attractive force, okay, attraction force, we call it gravitational force. So a force that is directly proportional to the product of m1 and m2 and inversely proportional to the distance. Now, when we look at the distance in chapter 7, the distance will start from the center of the object, the center of mass, okay, not from the surface. So from center to center, this is your R. Okay, so since it is the R between m1 and m2, now I can label it as R12. So you have object M1, object 2 with M2, and then the distance between them is R12. So according to the definitions, force, okay, now you're looking at gravitational force, therefore I'm going to give it a subscript G. Okay, subscript G. So Fg is directly proportional. So we are going to use a proportional symbol. So directly proportional, this is a proportional symbol, to M1, M2, the product of masses, and it is inversely proportional. So inversely proportional to R squared. Okay, so directly proportional, this is a symbol of directly proportional, A directly proportional to B. Inversely proportional, one of them would be a fraction. So the second one means inversely proportional. Okay, so this is inversely. And then this is directly. So make sure you understand what is the difference between them, because you're going to use them very often in explanations questions in physics. Okay, we use the terms, I would call these two magic terms. So in explanation questions, we often use these two magic terms to explain what is happening. Okay, to explain the relationship between two different variables. So in explanation questions in physics, we often use these two terms, directly proportional or inversely proportional, to explain the relationship. So now we combine them into one, and from here we then deduce an equation. So in calculations, you cannot have this proportion, this relationship, okay, because with a proportional symbol, okay, you cannot rearrange the equation. It's not you cannot rearrange, you cannot get an exact value. So to make it into an equations that can be used in our calculations, okay, so from these relations, we always add in a constant value to make it an equal equations, okay, to make it an equations with an equal sign. So from a proportional relationship equations, we want to transform it into an equations that can be used in our calculations. We add in a constant. And the constant that we added in this equation is G. Okay, it's a G, which is a universal gravitational constant. And the value is 6.67 times 10 to the power of negative 11. So this value will be given in the list of a constant. So don't have to memorize it. Okay, it will be given in the list of constants. So what you have to do, you just have to know when to use it, when to apply this constant value. All right. So remember, you from a definition. So this is what I call definition. From definitions, we have a relationship between F, M1, M2, and R. Okay, and from these relations, if you want to change it into an equations that can be used in calculations, often we add a constant. And the constant that is being added is G in this relationship. So F equals to G M1 M2 over R squared, where G is universal gravitational constant, which is equals to 6.67 times 10 to the power of negative 11. So remember, gravitational forces, gravitational force, it exists in between any two masses, including you and your friends, including you and the earth. Okay, and the reasons why you can standing on the earth, okay, this is the earth and this is you. The reasons why you can standing on it is because of the gravitational force. Now, why can't you feel the force between you and your friends? Or for example, between you and any objects around you. So you look at the values of G. So F equals to G M1 M2 divided by R squared. But if you look at the values of G, the things that you can observe is the power of G. Okay, G is equals to 6.67 times 10 to the power of negative 11. So if your mass is not heavy enough, then basically you won't feel the force between you and your friends. Okay, because force between you and your friend is very, very, very small due to this constant. This constant is 6.67 times 10 to the power of negative 11, which means if you want to feel the force in between you and your friends, then your mass, okay, should have up to times 10 to the power of 11 kg. Then you might feel a bit of it. Okay, and the reasons why you can feel the gravitational force, that is because the M of the earth is very, very, very heavy. Okay, it's very large compared to you. Okay, so the reasons why you can feel attractive force is not because of your mass, but it is because of the mass of the earth. Right? And the reasons why you cannot feel the force between you and your friends, you and your family members, that is because your mass is too small. Okay, and the effect is being cancelled out by this constant value. Okay, so if you want to feel the force, then you need to have something that is up to 10 to the power of 11 kg. Okay, now the second one, vectors from Newton's law of gravitation. So you want to sketch the diagram. So how to sketch the diagram? So you sketch the diagram. Okay, the force diagram. Okay, now because gravitational force is an attractive force, so the force in between M1 and M2, they are always pointing toward each other. All right, so usually I will just label F1 or F2, but in this examples given, okay, it uses F21 and F12. Okay, F21 and F12. So what is the relationship between F12 and F21? So F12 and F21, they are always opposite to each other. Okay, they are always opposite to each other with the same magnitude. So I would say F21 is equals to negative F12. So the minus sign in the equation is necessary because the force acting on the particle 1 due to the particle 2 is pointing towards the opposite direction. So this one, okay, this one, it gives you an equation. F21 is equals to negative G, not capital letter M, Gm1 M2 over R21. Okay, over R21. That is because of the directions of 2, 1. So your directions, we often look at the directions in the opposite direction. So the minus sign in the equation is necessary because the force on particle 1, okay, due to particle 2 works. Okay, so it's being attracted towards M2, but if you calculate the force, you use R21. So R21, the direction is opposite. Okay, the direction is opposite. So basically, this one, you just have to know the existence of this relationship. In calculations, we often look at the directions of R. Okay, we seldom look at the directions of R. Usually, we just look at the magnitude, and then we determine the directions based on the diagram given. All right, based on the force. So, okay, so bullet point C, okay, you just look at it. It's not very important. What we have to know is actually the following equation. So by Newton's third law, okay, by Newton's third law, the force F12, okay, acting on a M exerted by M1 must have the same magnitude. So the equations given here, now give you, if you have a negative F21, okay, you put a modulus, then the magnitude is equals to F12. Okay, the magnitude is equals to F12, which is equals to our Fg. So that is the things that I showed you just now. The magnitude between two objects. So let's say now you have object 1, object 2. So you have a force F21 and then the force F12. Okay, that is the force exerted on different particles. So which is equals to Gm1 m2 over r12. Okay, over r12. So the force exerted on object 1 is F21. Okay, this is the force exerted on object 1. If the question is asking for the force exerted on object 2, then it is F12. Now, there's another types of questions that can be asked in the questions in the exam, okay, which is force between. Okay, so force between, okay, force between M1 and M2 is just equals to Fg, okay, which is equals to Gm1 M2 over R12. So in that case, you don't have to look at the direction. Right? If the question is asking for the force acting on object 1, then you need to mention its direction. If the question is asking for the force acting on object 2, then you need to mention the direction. So the direction, you can give it based on the diagram given. And then if the question is asking the force between M1 and M2, then you don't have to state the direction. All right, so make sure you are clear. What is the difference between force acting on particle 1, force acting on particle 2, and force between particle 1 and particle 2? All right, if force acting on a certain particle, then you need to include its direction. So if the force between M1 and M2, then you just say they are being, they have an attractive force between them. Okay, they are being acted on each other. So the gravitational force is always attractive in nature, and the forces always act along the line joining the two masses. Okay, so that tells you what types of force it is. So it is an attractive force. All right. So now, how do we know whether an object experiences attractive force or not? Then we look at its gravitational field. If you place an object inside the gravitational field of the other object, then it can feel the gravitational force. Okay, so gravitational field is a space surrounding a body with mass. So let's say this is a object 1. So around this object 1, it has a field. Okay, it has a field up to a certain distance. So this is the field, right? This is a field. So if any other body, okay, with mass is placed inside this space, then it will experience an attractive gravitational force. So now let's say your object M, this red color M, it has a field which is in a blue color. And what you are doing now, you place another mass, okay, this green color mass inside this field. Then at that moment, these two objects, they will experience an attractive force in between them. But if you place a green color mass far enough, for example here, then there's no gravitational force between red color mass and the green color mass, because now this green color mass is not being placed inside the gravitational field of red color mass. All right, so that is a difference. That is when object can feel gravitational force, if you place it inside the gravitational field of the other masses. All right, if it is outside the gravitational field, then it won't feel anything. There's no forces between them. So field lines are used to show gravitational field around subject with masses. So we cannot simply draw a field, okay, like what I did here, the blue color field. No, actually that's wrong. Okay, I'm just showing you so that you can understand what does it mean. Okay, jangan lukis macam yang saya lukis dalam warna biru ini. Okay, warna biru ini saya cuma nak tunjuk kamu region, zone untuk gravitational field. So a proper way to sketch gravitational field line is as shown in the diagram given. So for spherical objects such as the Earth, the field is always pointing inwards, okay, as shown in the diagram. So for example, now this is your Earth, so coming with a capital letter M. Okay, so the field around this the Earth is pointing into the object, all right, into the object. So that is how you sketch it. Now, the gravitational field in a small region near the Earth's surface, they are uniform and can be drawn parallel to each other. So this is very, very close to the surface. Okay, very close to the surface. So then it will become a straight line. If it is far enough, then you will see a circle or a spherical shape. Okay, not circle, but a spherical shape gravitational field. So make sure you notice the difference. If it's far enough, okay, this is far, okay, far away. And then the second one is very close to the surface. Okay, so the line, the field line actually carry two meanings. The first thing is the arrow. Arrow, it represents the directions of the field. And then the spacing between the line, it represents the strength of the field. Now, what does it mean by spacing? Let's see if this is the Earth. Okay, and then you are drawing a line, okay, the field line beside it. Okay, so this is a field line. So the field lines that we have, for example, like this. Okay, so let's say now you want to place an object. If you place it close to the surface of the object, for example, now you place the object here. Now you can see there are three lines passes through this object. Okay, now when you have more line passes through an object, it means the spacing between the field line, they are smaller. In that case, okay, this object, blue color object, it experiences a greater field strength on it. Okay, it experiences a greater force on it. Now, if you place an object that is slightly further away from a field line, what you can see now, just have a two line that is merely touching the object, and the space between the line is much larger compared to the blue color object. Therefore, this green color object, it experiences a smaller field strength compared to the blue color object. Why? Because the field line passes through it, they have a larger spacing between them, and they are far away from each other. Okay, and you have a field line passes through the green color object. But if you look at the blue color object, the line passes through it. Okay, they have a more line, and the spacing between the line, they are smaller. Okay, they are closer to each other. Okay, so in other words, you can say that if you place an object close enough, closer to the Earth, then it will experience greater field strength compared to if you place it far away from the surface of the Earth. Okay, so that is the meanings of a field line. It tells you the strength of the field. Okay, whether the strength acting on the object is a larger or a smaller. So gravitational field strength, just now we look at it in terms of the line, in terms of a distance, the spacing between the line. Now we want to look at it in terms of calculations, in terms of value. So how to calculate? What is the definitions of gravitational field strength? So gravitational field strength is defined as a gravitational force per unit mass, okay, of a body that has mass placed at a point. So basically, you obtain this definition based on Newton's second law. Newton's second law tells you F equals to ma. Now you are looking at gravitational force, therefore Fg equals to mag. So rearrange these equations, you are going to get Ag equals to Fg over m. And this is the definitions of gravitational field strength. So basically, A is our gravitational field strength. So don't mix up with acceleration. In chapter 7, okay, we no longer call it acceleration, but we call it gravitational field strength. All right, gravitational field strength, which is Ag. So Ag equals to Fg over m, the gravitational force of a acting on a body, and mass is the mass of a body that has mass. So again, if you look at this object, okay, this equation, now you have to be careful with the m. The m uses in this equation is a mass of a body, a test mass. Now, what does it mean by test mass? Test mass is the mass that you can move around in the questions, okay, that usually we move around to test the value at different position. So for example, now this is the Earth, and then this is you. Okay, so you come with a small mass. So you are the mass that I can move around to test the gravitational field strength of the Earth. Okay, so usually we cannot move the Earth, right? So the Earth, we call it point mass. Okay, point mass is the mass that we usually we don't move. Okay, we won't move it in the questions. We leave it. And then test mass is the mass that we move around to test different value. So in this case, this smaller object, which is you, the human, is a test mass. So when it comes to the calculations, we don't use the mass of the Earth. We use the mass of the objects around it, which is you, or maybe a satellite. Okay, satellite is the things that we move around the Earth. So this is our test mass. Okay, the mass that we can move around to test different value, and they might experience different gravitational field strength. So now in that case, what does it mean? So it means if you look at the questions, okay, so AG is equals to FG over M. M is the mass of your test mass, okay, it's the mass of you. So force is the gravitational force. So if you're standing on the surface of the Earth, then AG is actually equals to your gravitational force, your G, okay, your gravitational accelerations, the accelerations due to gravitational force. So AG is equals to the G on the surface of the Earth, all right, if you're standing on the Earth. So basically, this AG, okay, is the accelerations due to gravitational force. So in chapter 7, we call it gravitational field strength. In chapter 4, we call it G. So you see, same thing, but in different chapter, we give it different name. So you don't get confused. Okay, you don't get confused between them. So since gravitational force is a vector quantity, and gravitational field strength is also a vector quantity. Okay, because now you use a vector quantity divided by a scalar quantity, therefore A is also a vector quantity. So what is the unit? The unit is just ms negative 2, same as your acceleration. So it is also known as gravitational acceleration. But most of the time, the question will address it, will call it gravitational field strength. Its direction is in the same direction as the gravitational force. All right, so it is an attractive force. Okay, so gravitational field strength at a point. So now you want to look at the gravitational field strength at a point, but not just the surface of the Earth. So what are we going to do? We sub Fg equals to Gmm over r squared. So basically, this m, capital letter M and small letter m, they carry different meaning. Capital letter M, it stands for point mass. Okay, point mass, which is the mass that is not moving. Small letter m is the test mass. Okay, the mass that usually we move around, that can be moved around in the situations given. So Ag equals to F divided by test mass. Okay, test mass. And then which is equals to 1 over m times Gmm over r2. So if you look at this equation, what happened is test mass, they are being cancelled out. So if you look at Ag at the same time is equals to G capital letter M over R squared. So for the same equations Ag, you have two different equations, and two of them, they uses different mass. So make sure you choose the right mass in your calculation. So Ag, the first Ag is Fg divided by small letter m. The second Ag is G capital letter M divided by R squared. So two of them, they uses different M. This is the part that you have to be extra careful when it comes to the calculations questions. Small letter m is test mass, the mass that can be moved around in the situations given. And then capital letter M is the point mass. Okay, usually it refers to the planet. So in a chapter 7, usually we'll have cases where you have an object and then you have a human standing on it. So this is capital letter M. So a human is a small letter m. Or a second case given capital letter M with a satellite. So this is the usual examples that we have in our questions. Okay, situasi yang biasanya kita ada. Okay, satu melibatkan orang, manusia, satu melibatkan satellite. So satellite is a small m. So if you want to calculate AG by using the first equation, then the mass, you use a small m. If you want to calculate the AG by using second equations, okay, then you use the mass of the planet. Okay, usually it's the mass of the Earth, okay, or the mass of the moon, and so on. So make sure you know which m to use in your calculation. So gravitational field strength at a distance r from a center of the planet. So figure shows the directions of the gravitational field strength from the center of the planet. So now if you place an object that is above the surface area, the surface of the Earth, then what is going on? You can calculate it by using Ag equals to Gm over r squared. Okay, so this is the equation that we derived just now. So this equation is valid for any object that is above the surface of the Earth. All right, so as long as it is above the surface, then we can use this equation. Ag equals to Gm over r squared. Now, if you place it at the surface, okay, at the surface or on the surface of the Earth, then what is going to happen? So the gravitational field strength in a small region near the Earth, okay, where we call r equals to capital letter R. So capital letter R is the radius of the Earth. So now this is the Earth. So for Earth, we use capital letter M, and then the radius, we use capital letter R. Okay, for planet, usually we use a capital letter. So they are uniform where the strength, so because now when it's very close to the surface of the Earth, we assume the gravitational field line is a uniform set of field line as shown in the figure. So when it's close, very, very close to the surface, okay, we assume it has a constant value, which is equal to 9.81 ms negative 2. And the direction is always pointing downwards. That's why when you calculate Fg, the force is always pointing down. That is because our Ag is always pointing downwards. Okay, and because when it's very close to the surface, okay, we assume the gravitational field line is a set of uniform line. Therefore, it has a constant value where G is equal to 9.81 ms negative 2. Okay, so because we assume it's uniform, therefore we assume it has a constant value when it is close to the surface of the Earth. When it is far away, then it's no longer uniform. Then you have to calculate it by using Ag equals to Gm over r squared, right? Now, what happens if it is inside the field? So if it is inside the field, inside the surface, sorry, not inside the field. If it is inside the surface area, for example, if it's inside the object, okay, then you can no longer use the equations that you derived just now. Okay, so equations yang kamu derive, dia tak valid untuk distance inside the field, inside the surface. Alright, so that one is no longer in your syllabus. Therefore, I won't show you the equations. What you have to know, okay, is if it is on the surface, then you have G equals to 9.81. Okay, so this is on the surface. So when it is above the surface, okay, above the surface, okay, above the surface, then we apply equations. A equals to G m over r squared. Okay, therefore the relationship between A and R is A is inversely proportional to r squared. Right? When it is inside the surface area, the only things that you have to know is the relationship between A and R, they are directly proportional. So you have three types of values in the A against R graph. So this graph you have to know, okay? This graph, it shows you the relationship between A and R. So when you're at the center of the object, okay, of the mass, then A is equal to 0. As it gets further away from the center of the mass, the relationship between A and R is they are directly proportional to each other. Therefore, you get a straight line until it reaches the surface of the Earth. Okay, so this is on the surface. Okay, it is exactly right at the surface of the Earth. So at this point, if you are looking at the Earth, then this R is the radius of the Earth. All right, and G is equals to 9.81. But this is only for Earth. Right? If you are sketching the graph for example, other planet, Mars, Pluto, then you cannot write this value anymore. All right. This value you only include it in your graph if you're sketching it for the Earth. If you're not sketching it for the Earth, you're sketching the graph for the other planet, well, you will still have the same shape, but you don't include this value. Okay, boleh faham? Kalau kamu lukis untuk bumi, kamu kena masukkan nilai 9.81 and then kena masukkan RE punya nilai, sekiranya diberi. Okay, tetapi kalau anda tengok pada planet yang lain, then apa yang anda buat? You just substitute as AG. Okay, you don't substitute as G anymore, and then this R, you just substitute a capital letter R without the small subscript E. Okay, because you just want to tell people that now this is the radius of the planet given. Okay, so it is a straight line until it reaches the surface, and then it becomes a inversely proportional graph. So this part is A is inversely proportional to R squared. So this graph basically is being split into 3 sections. First section, directly proportional. Second section, you have the value. And then the third section is inversely proportional. All right. And when you sketch the graph, there's one very important thing. Don't let it touch x-axis. Okay, don't touch. Why? Because it will take infinitely long distance to reach 0. So basically, okay, it doesn't matter where did you place the object, it will feel the gravitational force, it will feel the gravitational field strength. Okay, because this graph, it will touch x-axis at infinity. Okay, so macam kamu mathematics, like your mathematics, you have a limit. So this is the limit. It won't touch. Okay, it won't touch the x-axis. So this is the things that you have to be careful when you sketch the graph. So graph sketching is a very popular question in the exam. Make sure you know how to sketch the graph. And don't let it touch x-axis. It will never touch. It will touch it at infinity. Okay, so you just draw it very close to x-axis, but don't touch the x-axis. Right, next. So gravitational potential energy. Now, if you recall this term, actually we have already learned it in chapter 5, gravitational potential energy. In chapter 5, we say UG is equals to mgh. Okay, so UG is equals to mgh is only valid when you place the object on the surface. Okay, on the surface of the Earth, where we assume the gravitational field line, they are uniform to each other. Okay, when they are very close to the surface of the Earth, then we use UG equals to mgh. But now in chapter 7, okay, we often look at the object that is very, very far away from the surface. So in that case, we have to use a different set of equation. Okay, so gravitational potential energy is defined as the work done by an external force in bringing a test mass from infinity to a point. So now you have an object, M, okay, this is a mass. So initially there is nothing around it. Okay, there is nothing around the object. So what are you going to do? Now you want to place an object inside its gravitational field. So the energy, the work done, the work need to be done to place another mass inside the gravitational field. Okay, then we call it gravitational potential energy. Okay, the work done to bring an object from infinity to a point inside a gravitational field. That is gravitational potential energy. So given work done in bringing a test mass from a point to another is W equals to negative GMM over 1 R final minus R initial. By combining the idea above, okay, because now you are bringing the object from infinity, so your R initial is infinity, and then this is your R final. So R final is a non-zero value. It is the distance between your capital letter M and the small letter m. Okay, the point mass and the test mass. So by combining the idea with the equations above, so this is the equations for work done from one point, okay, work from 1 point to another point inside gravitational field. Gravitational field. But when it comes to the definition, you're looking at from infinity. So this is the equation for from infinity. Infinity. Okay. So one is from one point to another point, the first equations, and then the second equation is from infinity. So you substitute R initial as infinity. Okay, R initial as infinity. So what happens when you divide a value with infinity? So 1 over infinity is actually equals to 0. So basically, this part is equals to 0. So when it is equals to 0, what can you do? So we get W equals to negative GMM over just 1R, which is the distance between point mass and test mass. Okay, the distance between point mass and test mass. So the other R is gone because it's infinity. So 1 divided by infinity is 0. Okay, so when it comes to gravitational potential energy, we call it U. So U equals to W equals to negative GMM over R. All right, so far clear? So pastikan Anda tahu, okay, make sure you know when to use capital letter R, when to use small letter r, and then when to use which equations. First equation is for work done between 2 points inside gravitational field. The second one is the definition. Okay, this is the definition. And then definition, it tells you the object initially is coming from infinity. So you substitute R initial as infinity. So if it is not infinity, then you substitute the value. Then it will go back to the first equation, right? So U equals to W equals to negative GMM over R. So why GMM over R? Because when you use 1 divided by infinity, then it will give you 0. Okay, it will give you 0. Okay, so we are done with gravitational potential energy. So gravitational potential energy, it just tells you the energy needed to bring one object from outside gravitational field into a gravitational field. Okay, so now what happened next is we want to look at a new thing called escape velocity. So just now we want to place something inside gravitational field. Okay, now we want to look at what if you want to leave the gravitational field. What if you want to leave now? Just now we place it inside gravitational field. Now we want to run away from the gravitational field. So escape velocity is defined as the minimum velocity required by a mass to escape completely from the gravitational field to infinity. Okay, it wants to escape from field to infinity. So maybe it's just one step away. Okay, maybe it's very far, very close to a object, and maybe it's just a one step away to leave the gravitational field. So now what we want to do, we want to calculate the velocity needed to run away from a planet. Okay, to run away from planet. So at infinity, the gravitational potential energy is no longer a value, it is equal to 0. Why? Because it has already escaped. Okay, it has already escaped from the gravitational field. Therefore, gravitational field strength is now equal to 0. Okay, so it won't fuse any energy. No energy is needed anymore. And the final kinetic energy of this mass is given by K is either greater or equal to 0. So when it escaped from the object already, then we are going to look at the energy, the V that is equal to 0. Okay, the V is not equal to 0, sorry. The kinetic energy that is equal to 0. So the final kinetic energy is equal to 0. So by using the principles of conservation of energy, we have K initial plus U initial equals to K final plus U final. So U definitely is equal to 0 because it has already left the object. Okay, and then K, the kinetic energy of the mass is given. So once it escapes from the object, it might no longer move. So K is also equal to 0. Therefore, what we have is just what happens inside the planet. Okay, inside the gravitational field. So initial kinetic energy, okay, so now you have an object, and then this object is trying to run away. Okay, so it's moved with an velocity. Okay, it moved with velocity. So it tried to escape. So this is your K initial, and then also U initial. So it's moving. Okay, it's moving. Maybe it's moving along the orbit. Okay, it's moving along the orbit. And now it wants to run away from this orbit. So when it's moving, of course, it has a velocity, and then it has a gravitational potential energy. All right, it has a gravitational potential energy. So assuming an object is attempting to escape from a uniform spherical planet by moving away from it, okay, the only force that is moving the object is the planet gravity. So we are looking at the initial speed. Okay, we're looking at initial speed. Okay, now what happened now if object escape from this, okay, escape from this orbit, then what is happening is now we assume u final is equal to 0 because now it's no longer inside the gravitational field, and then k final is also equal to 0. Why? Because when it leaves the planet, then we can assume the v is very, very small now because there's no force causes the object to move anymore. Okay, so it might just floating in the space. All right, so we assume it is close to 0. Okay, therefore in our calculation we substitute it as 0 plus 0. So k initial half mv squared plus negative gmm over r equals to 0. So 1 over 2 me squared equals to gmm over r. So by rearranging the equations, what you can see is small letter m, they are being cancelled out again. So it is very important. Okay, small letter m, they are being cancelled out again. What you have right now is just VE equals to, okay, equals to square root GM over R. Okay, GM over R. So VE equals to square root GM over R. Wait, yeah. Oh, there is a 2 here. That's a mistake. Wait. 2G capital letter M over R. Okay, over R. So V is the escape velocity, and then G, of course, is the constant. M, capital letter M, is the mass of the planet. Okay, it's the mass of the planet. And then R is the distance between test mass. Now, what can you tell from this equation? Okay, what can you tell from these equations? Basically, this equation, it tells you the mass of the object, okay, the test mass is not important. So it doesn't matter whether you're looking at a human, you're looking at a satellite, or what is the other objects that you're looking at. All of them, they will have same escape velocity. Because escape velocity, it doesn't depend on the test mass. It depends just on the mass of the planet, the point mass. Okay, the point mass. So regardless of the object that you're looking at, all of them, they're going to have the same escape velocity. Okay, so sometimes questions might ask you, now you have an object A and object B. So what is the escape velocity for object A? What is the escape velocity for object B? Okay, so if both of them, they have same R, then the escape velocity will be the same, even though they might have a different mass. Okay, so let's say, okay, I'm going to erase this first. So now let's say now you have an orbit. Okay, so this is the orbit. So let's say now I have object A, which is m is equals to 1000 kg. And then I have another object B, where it's m is equals to 5000 kg. So question asks you to calculate the escape velocity for them. Now, since two of them, they have the same R, okay, then escape velocity for object A is equal to escape velocity for object B. Why? Because it doesn't depend on the mass of the object. It depends on the point mass of the planet. Okay, the point mass of the planet. All right. So this is what you can tell from the equation. Okay, which it doesn't depend on the mass of the test mass, test object. Now, if the test mass is on the Earth's surface, then R is equals to capital letter R. Okay, so usually, like I told you just now, capital letter R, we use it to represent the radius of the planet. Okay, capital letter R is the radius of the planet. And then small letter r is the distance between two masses. Okay, small letter r is the radius between two small masses. So VE is equal to square root 2gm over capital letter R now because you place it on the Earth's surface. And we know that GM is equal to GR squared. Now, where does it come from? So where does it come from? So we know AG is equals to GM over R. So if you look at the surface, the Earth's surface, so at the surface of the Earth, we have AG equals to G, and then we have R equals to R. So by substituting the equations, okay, it into the equations, we have G equals to GM over capital letter R. Rearrange the equations, GR square. Okay, GR square equals to GM. So this is how you obtain this relationship. Okay, so this only happens on the surface of the Earth. So VE equals to square root 2 GM over R, and GM equals to GR square. So sub it into the equations, R and R cancel out. What do you have? You have VE straight away equals to square root 2 GR. So it is even simple. Okay, it's even simple if you place an object on the surface. Then straight away it is equal to square root 2 times 9.81 times the radius of the Earth. So again, you see, test mass, it doesn't affect the value. Okay, the things that affects the value is the radius of the Earth. Okay, the radius of the planet. So this is the escape velocity. All right, so let's recall gravitational potential energy. It refers to the work done in bringing some object from outside the field into the field. Escape velocity is now your object is trying to escape from the field. Okay, it tries to leave the field. So there are two different things. All right, don't get confused between them. So done. Okay, this is the escape velocity. Escape velocity, it doesn't depend on test mass. It depends on the point mass. Okay, it depends on the point mass. So last part. Okay, last part. So derive the equations for the satellite motion. So satellite motions, you can say it is a question that comes out in exam every year. Right? It asks you to either calculate the velocity of the satellite or the period. Okay, the time taken to to move one circle around the planet. Okay, to complete one orbit. So figure shows a geostationary, okay, the synchronous satellite, which stay above the same point on the equator of the Earth. So the satellite has the following characteristic. It revolves in the same directions of the Earth, and then it rotates with the same period of the rotations of the Earth, so 24 hours for one circle. It moves directly above the equator, and then the centers of geostationary synchronous satellite orbits at the Earth is at the center of the Earth. So this characteristic is only valid for geostationary satellite, which is a synchronous satellite. Okay, so kamu kena berhati-hati. Kalau dia bagi kamu perkataan geostationary satellite or synchronous satellite, okay, then what happened? It has a period that is equal to 24 hours. That is what it wants to tell you. Okay, that is what it wants to tell you. Now it moves directly above the equator, and the center of geostationary is at the center of the Earth. All right. So apa yang dia bagi tahu kamu? The most important thing is 24 hours for one circle if you have a geostationary satellite. But if it is not a geostationary satellite, then what is going to happen? So the centripetal force contributed by the gravitational force of attraction force. Now you have an object. Okay, this is a planet. And then you have a satellite. Okay, you have a satellite. Satellite is moving along the orbit. But if you look at the shape of the orbits, it is a circle. Okay, it is a circle, which means this satellite is actually moving in circular motion. Aha. Okay, it's moving in a circular motions. So in a chapter 6, we know that F net force is equals to MAC. Okay, so what is happening here? FC is also equals to mv squared over r. And this mass is the test mass, okay? The object that is moving, the mass for the object that is moving. Now in chapter 6, okay, we always says we want to keep the equations on the, okay, the part of the equations on the right-hand side. Then we expand the left-hand side of the equation. So FC is the force that causes object to move, okay? The force that causes object to move in circular motion. okay, to move in circular motion. So in this case, the force that causes my satellite to move in a circular motion is the gravitational force. Therefore, Fg is equals to mv squared over r. So Fg, okay, Fg, what we know is Fg, according to our derivation just now, is equals to G mm over r squared. So sub it into the equation. We have G mm over r squared equals to mv squared over r. Aha. So again, if you look at the equation, the terms that is being cancelled out is the test mass. Okay, test mass and cancel out. Then the remaining terms that I have is the equations for velocity of the satellite. Okay, it's the equations for the velocity of the satellite, which is v equals to square root gm over r. So this is the equation in our first box. Okay, v equals to square root gm over r. So be careful, this is not escape velocity. All right, this is not escape velocity. Escape velocity is v equals to square root 2gm over r. Okay, this is just a normal velocity. This is a velocity for satellite. Okay. So this is the velocity for satellite, not escape velocity. Don't get confused. Escape velocity is the velocity that can makes the satellite to move away from its orbit. Okay, to escape from its orbit. If it is going to move along the orbit, then we use this velocity. Okay, so this is the difference between the velocity that we are using now and the escape velocity. The velocity that we are using right now, v equals to square root gm over r, is the velocity for this satellite to move along the orbit. If you are looking at escape velocity, then it will leave the orbit. So it will leave the orbit with escape velocity. Okay, but it is moving in the orbit with this velocity. Okay, so jangan keliru ya, jangan keliru. Make sure you read the questions carefully. So the relationship between the tangential velocity and the angular velocity is v equals to r omega. So this is what we learned in the chapter 6. So r omega at the same time is also equals to 2 pi r over t. So v other than equals to square root gm over r, when you are looking at the velocity in a circular motion, it is also equals to 2 pi r over t. Okay, so 2 pi r over t equals to square root gm over r. Therefore, by rearranging the equations, you can obtain the period, which is equals to 2 pi square root gm over r cube. Okay, sorry, terbalik. Not gm over r cube over gm. Okay, r cube over gm.
Madam,
Yes.
macam mana omega tu dapat 2 pi per t?
Omega dapat 2 pi per t, itu kan kamu sudah tengok di chapter 6. Chapter 6, it tells you omega equals to 2 pi f. It tells you t equals to 1 over f. By combining these two, then you obtain omega equals to 2 pi over t.
Oh, okay. Thank you, madam.
So from these equations, you rearrange and you obtain period is equals to 2 pi square root r cube over gm. Okay, r cube over gm. Now, how to get this r cube? This is a question that students like to ask. So how to obtain this r cube? So now you have 2 pi r over t equals to square root gm over r, right? So what we want to do, now I want to rearrange the equations, therefore I'm going to flip it over. So t over 2 pi r equals to square root r over gm. Okay, I flip it over first to make it easier for me to rearrange the equation. So t is then equals to 2 pi r square root r over gm. Now you want to move this r into the square root. Okay, you want to move this r into a square root. So what you can do, okay, we know that r square, okay, r square is equals, square root r square is equals to r. Okay, so therefore these equations can then be written as t equals to 2 pi square root r square times square root r over gm. Okay, over gm. So square root r square multiplies square root r over gm. It is then equals to 2 pi square root r square times r cubed over gm. Okay, so when you have square root and square root, you can multiply the terms inside it. Okay, so when you have a square root a times square root b, it is actually equals to square root a times b. So this is a simple mathematics. So this is what happens here. So you use a r square times r. Therefore, you obtain r cubed. Okay, therefore you obtain r cubed. So ini soalan yang pelajar setiap tahun tanya. So make sure you know how to obtain this r cubed. It is actually the simple mathematics where you multiply two square root together. All right. So that marks the end of chapter 7. Okay, that marks the end of chapter 7. So do you have any questions? Basically, it's involved more of the definitions, derivations of the equations. How to use it? Okay, you have to practice it in a tutorial class. So right now, your task is to know what is the difference between these four characters. Capital letter M, small letter m. Capital letter R, small letter r. Okay, so capital letter M, it refers to point mass. Small letter m is test mass. Capital letter R is the radius. Small letter r is the distance between two masses. All right, so your first task is to remember these four terms, these four variables. So that's the end for today's class. All right, if you have any questions, you may ask. If you don't have any questions, then you may leave the class now.